Hello everyone, good afternoon. Dear authors and invited guests, welcome to Technical Session 12D. Myself Sirali Gaur and this session would be moderated by me. On behalf of Global Knowledge Research Foundation and GIA Scholastic, it is my great pleasure to welcome you to the 11th International Conference on Information and Communications Technology for Sustainable Development, ICT4SD 2026, Goa, India. The 11th edition of the conference is being organized in a hybrid mode. The physical event is being held today on 11th of July 2026 in Goa, India, and the virtual event is being held through Zoom from 9 to 11 July. I hope you will enjoy the knowledgeable and interactive session throughout the day. In this session, we have a total of 10 presentations. Each presenter will be given 10 minutes for their presentation and 2 minutes for question and answers. On the 9-minute mark, I will raise a gentle reminder. If you have any query or any update, please write to me in the chat box. There is also one more request to all the participants that you stay connected with us till the closing remarks. Just before we start the session, I would like to introduce you all to the chair for this session today, Dr. Ajay Kumar Sharma. Dr. Ajay is a professor and MTech program head in the Department of Computer Science and Engineering at Gitanjali Institute of Technical Studies, Udaipur, Rajasthan. With over 18 years of teaching experience, he has presented numerous papers in national and international journals, conference and symphoniums. He has also served as a reviewer for more than 15 years in IEEE and Scopus indexed conferences and journals. I welcome you, sir, today. Before we start the session, do you have anything you would like to say?
Hello. Yes. Good afternoon to all, respected speakers, chairs, dear participants. It's my great privilege to serve as a session chair for this session of 11th International Conference on ICT for Sustainable Development. I sincerely thank the organizing committee for their dedications and outstanding effort in making this conference as success. My appreciation goes to our moderator, Ms. God, for this efficient coordinating the session. And very special thanks to Dr. Amit Joshi, sir, for his valuable guidance and continued support. I encourage all the participants to actively engage in discussion and share their insights. Thank you. I wish everyone a productive and insight session. Thank you.
Thank you so much, sir. Let's begin with our presentation for today. First, we have Pallavi Sonawale with the paper title A Deep Learning Based Explainable Framework for Multi Cancer Detection Using CNN and XAI. Dear presenter, you may start presenting.
Hello all. My name is Pallavi Sonawade, and my topic name is Explainable AI for Multi-Cancer Detection. So basically, what is explainable AI? Explainable AI is like a basic black box model which can give explanation to decisions for AI model makes. So in early stages, so for example, in for cancer treatment, early and accurate detection for that particular disease is very important because delay in detection of cancer can cause multiple complications for patient as well as doctors also. So with the help of explainable AI, which can give accurate explanations to that medical decisions, we can develop the transparency and make it transparent and interpretable model. And the motivation for this is like early cancer stages have high stakes challenges, demands the best human expertise and technological power. So the this project addresses main key limitation for lack of interpretability in black box models, rather than improving like diagnostic accuracy or anything like that. Explainable AI framework reveals the thinking of an AI, particular AI model, why it occur, it is giving that particular decision, why reasoning behind that particular decision. So basically, I have done literature survey on multiple papers. Some of them are some of them are included here. So basically, the first paper, which is for lung cancer, and the technology they have used is CNN, federated learning, and explainable AI. The main disadvantage in this technology is like data set imager. They have included limited size of data set. Second is for like fusion machine learning black box model is for like multiple methods, and they have used explainable AI frameworks and neural networks for that. So the main problem for this paper is like scalability and limited data sets. Third is for the breast cancer, and although it provides high accuracy, but it cannot generalize well with complex or real time clinical data, which is very important in terms of medical or healthcare section. Fourth is for deep learning based approach for cancer classification, and they have used deep learning and explainable AI. So overall, they have achieved 66% of balance accuracy. In my fifth paper, I have used a skin cancer detection classification model. So they have used similarly used explainable AI technologies, which is for GradCam plus and SHAP and Lime. So basically, GradCam and Lime provide the explainability for our AI model, which explains the decisions which explains the decisions making by AI models. Due to the complexity of GradCam plus and their CNN model VGGNet, the model becomes more complex, and the performance comparatively is lower. So similarly, for sixth model, they have used lung cancer. For lung cancer, they have used CNN and Lyme and Sharp. Outstanding accuracy they have achieved around 99.63. But as I said earlier, if we have we have used higher accuracy, they get higher accuracy. Their chances of getting model complex and increase. There is a increase in complexity. Seventh paper is seventh paper is for like cervical cancer. So they have also they have used VGGNet and XAI, which is explainable AI. They have used GradCam and LRP, which is for transparency and interpretability for clinical trust. And due to its complexity, due to its increased complexity, the results are comparatively lower. Then along with that, VGG and support vector machine they have used for like cervical cancer. So they have achieved a transparency and interpretability via XAI. So the main disadvantage, or what I say, main research gap I have observed in that all papers is that all the models or all the papers I have researched, they have included only one type of cancer. Like only they have research on like one type of cancer or one model that can detect that. So and but in real life we cannot detect one cancer. There are multiple types of cancer. So in terms of black box model, the AI model can detect multiple cancer type, which increase the overall interpretability and transparency. So the objective is to simple objective is to build the AI model that can detect multiple cancer types from medical data, and using explainable AI framework, which is like GradCam and Lime, so they can interpret the decision made by the AI model. So The project develops a explainable AI framework for multi-cancer detection that combines high diagnostic accuracy with interpretable predictions, enabling clinicians to understand, trust the model decision, and support informed clinical decision making. So basically, architecture is simple. If we provide input data like the database, which consists of medical images like MRI, CT scan, or different the images required for different cancer types, uh, which is fed to the model. Then basic pre-processing to sort that data, then applying feature extraction CNN model, then classification of the cancer cell and non-cancer cell, and applying on basis of that applying explainability module to that decisions, so it can generate accurate response or give accurate predictions or accurate reasoning behind that decision of an AI model and give that decisions to us. So as I said, for input I have given them medical images or test results which consist of MRI, CT scan, biopsies, or any image data. And for pre-processing, data cleaning and data reduction I have used. For feature extraction, CNN ResNet model I have used. Classification, fully connected classification layer. And for explainability module, Lime and GradCam, which is for explainability, which gives the reasoning behind the AI models. So for the data set I have used Kaggle cancer data set, which consists of like multiple different types of cancer, like brain cancer, lung cancer, skin cancer, breast cancer, and etc. So converted them into two classes for tumor cell and normal, which consist of 5,000 of images each. For pre-processing, data cleaning, normalization, and noise reduction to uh, to for the better data set. And feature extraction and classification is used to extract the meaningful patterns and features from medical images and consider on only main part of an image. An exploratory model interpret the visualization and interpret the how the AI model made its decision. The images consist of medical images for cancer detection and classification. Each data set for each cancer type consists of 10,000 images, including and they have further two classes for normal and tumor. For each classes, for normal it has 5,000 images, and for tumor it has around 5,000 images, and all the images are resized into 300 into 300 pixels, and the images are basically in the standard JPG PNG format. Data set splitting I have done into 70 to 30, which is for 70% for training data and 30% for validation data. Images were processed in batches of 32 samples for efficient training, and during that training of images, I have saved the best results in that. In convolutional neural network, basically is used for feature extraction and classification. So basically one image is the feature is extracted from medical image and classified them into cancer and non-cancer data, say cancer and non-cancer image. So
Dear
model training
presenter,
efficient. Yes, ma'am.
I'm sorry to interrupt, but you have crossed your 9-minute mark. Kindly conclude your presentation soon.
Yeah, sure. uh, During model training, efficient net was used, and global average pooling layer is added extra high level features. A dropout layer used for reduce overfitting, and dense output layer is for sigmoid activation. The model was trained using Adam optimizer and binary cross entropy for loss function. Um, so this is the layer, and this is the training across the epoch. Performance matrices I have used accuracy, precision, recall, F1 score. Performance evaluation and overall 0.94 accuracy I have achieved, which converts them into normal and tumor. So for confusion matrix analysis, it can truly detect 1543 normal images were correctly classified as normal, and uh, 1284 tumor images were correctly classified as tumor. uh, in explainable AI, as I said earlier, explainable AI frameworks I have used is GradCam and Lime, which is for Lime goes for like a basic reasoning, and GradCam visualizes the results given by the AI model. So basically, it generates overall heat map. GradCam generates the overall heat map, and highlights the important region where the tumor can be. So like warmer shades of red and yellow indicates the higher regions or higher chance of getting the tumor, and the blue indicates the area which has low importance. For Lime, it gives reasoning behind the AI model and highlights the important or like important segments of an organ or like area which can have cancer. So in conclusion, we can it understand clinicians can understand and trust AI driven predictions better, and future it can develop a future clinical integration and detect a real time cancer diagnosis. And the future scope, in future we can use a larger data set and take a multiple scans or test for cancer, but depending upon the cancer types. And it can enable the multi cancer detection, and do the tumor stage prediction. These are the references of the research papers I have used. Thank you.
Thank you. Do we have any questions?
Miss Balwin, first of all, nice
Yes, sir.
presentations. My
Thank you, sir.
question is that what data set do you use for training and testing?
So basically, I have used Kaggle Cancer Care dataset. Basically, it has like multiple cancer types. So on that, I have used brain cancer, lung cancer, and cervical, breast cancer, and kidney cancer. So they have each have multiple classes in them, and I converted that images into two classes, which is for tumor and normal. So on that I have used like around 10k of images they each class have, and I have used that images.
What is your main limitations of your proposed framework?
So basically my proposed system basically uses the images, or the basically have images of data set. So but cancer can have multiple clinical tests they have to conduct. So in future, if we develop the model further, we need to collect that multiple tests and develop the model according to it. It can, for now it can detect only basis of the imagical data I have provided.
Can your model be deployed in real clinical environment?
Yeah, it can be developed in a real time clinical environment, but it has to train on diverse, like a very diverse data set and very diverse images. So we have to consider that fact also according to in times of real time deployment.
What's your size of data set?
It has like around the total data set of different classes. It has around 8 GB or 9 GB.
Okay, thank you.
Thank you
Thank you,
so
sir.
much. Next, we have Shardul Brahmanatkar with the paper title AI Tutor for Visually Impaired Learners Review and Implementation. Dear presenter, you may start presenting.
Uh, just a moment. Is my screen visible?
Yes, sir.
Thank you. So, good afternoon, everyone. This is Shardul Brahmanapkar from Pune Institute of Computer Technology. I am presenting a paper titled AI Tutor for Visually Impaired Students, Review and Implementation. Along with me, my co-authors are Pranali Lokhande, Anurag Thorat, and Bhakti Kadam. This would be our agenda for today. Uh, AI tutor for visually impaired students. Visually impaired students have difficulty in accessing traditional educational resources, which are heavy in textbooks and context heavy. To make this education accessible for them, we have thought of what technologies we can use in current age and era. So the proposed system uses RAG, which is retrieval augmented generation, to help visually impaired students have an interactive tutor to learn STEM concepts. Till date, all the systems which have been developed are mostly focused on tactile or IoT based. The systems, tactile based, are 3D printed maps, puzzles, which can help visually impaired learners to feel the object and know their shape and feel. IoT based help visually impaired learners to learn the Braille concepts, and also efforts have been made to integrate CNN and or image based helping for the visually impaired student. In our problem statement, we have tried to create an interactive tutor which can communicate with the student and explain them the exact concept they want to learn. For example, inheritance can be different in biology and it can be different in programming. In biology, inheritance is the genes which are transferred to the next generation, and in programming, it is the class which inherits the parent class properties. So to address this, we have made use of RAG, which I will explain in further. So the proposed methodology in this, we have made use of speech to text. For this, we have tested two models. One is Google's API and other is OpenAI's Whisper model. Whisper model works locally on a laptop system, and Google's API is cloud-based, which is fast in has lower latency to provide output. For RAG, we have made use of Llama 3.18b model, and our proposed architecture is multimodal as it provides output in form of audio as well as in form of Braille. The proposed architecture of our system is the system captures the query of student. Query is then converted from speech to text. Once speech to text is converted, then we have made use of RAG. RAG then uses cosine similarity search to find the exact answer for the user's query. And then by using LLM, we have generated the answer in form of text, and then text is converted to speech and Braille. So how RAG works is we ingest data to the RAG. We can ingest Excel files, textbooks, or databases in that. The whole database, like textbook, is converted into chunks. The chunks are stored either in ChromaDB or FAISF, and those chunks are then stored as embeddings, for which we have made use of all mini LM L6v2, which stores the embeddings, and this is the vector storage database. For mathematical, word error rate is the error rate which our model calculates. So S is the substitution, which the word is spoken. D is the deletions, which are omitted by the model. I is the insertions. And the minimum the word error rate, the more accurate our model is in interpreting our speech and text. Cosine similarity, it is nothing but a vector A is the input query which is given. Vector B is the query which is similar to the input query. And it is the dot product divided by the magnitude of the both vectors. For hardware, we have made use of i5 processor laptop with 16 GB RAM and 512 GB SSD. For our software stack, it is Python LangChain, all mini LM L6v2 embedding model, and fast vector store. For processing pipeline, we have made use of Grok's open source language processing engine. For our results, Whisper has denoted that it has higher latency, but it has higher latency of 10.15 seconds and a word error rate of 0.281, but it guarantees the data privacy and offline capabilities. That is, it works on the student system itself. Google Cloud API, it has a lower latency, which is of 2.76 seconds, and better accuracy and of word error rate, which is 0.025, but it requires internet to function. And for our rack testing, we have tested it on two core engineering domains. One is electronics engineering and the other is cellular networks. For electronics engineering, we observed that the response time for the model was 0.38 seconds. And for cellular networks, it was 8.5 seconds. Our results are listed in tabular format. For conclusion, we have tried to develop a system which can help visually impaired students learn in a better way and have STEM education accessible to them in a Braille format as well as in voice format. For now, there are Alexa, Claude, and other existing AI technologies in the market, but they have the limitation of token and context. This is why we have made use of RAC to conquer them. Thank you.
Nice presentation, Cyril. Hello.
Hello.
Nice presentation, first of all.
Thank you.
My question is that how does your system support voice integration?
For voice integration, we have Whisper, OpenAI's Whisper model, which uses the input from the user, and that user's input is then converted from speech to text, and that text is then used for further processing.
Okay. Any limitations of your project?
Currently, yes, it is a prototype which we have developed, but you can say that Whisper model is slower, but why we have made use of it. But Whisper is slower, but it provides the privacy of audio of the student, which we felt was important. And that is why we made use of Whisper and not the Google API. Though the latency of Whisper is more, but privacy is more important from student perspective.
Can the system work offline?
Yes, with you, not totally as of now, because the Grok utilizes internet and it needs internet, but the voice part can work fully offline.
Thank you.
Thank you.
Thank you so much. Now we have Deepa M with the paper title Assessment of Viability of Unified Large Language Models Ecosystems for Affordable and Reliable Utilizations by Gen Z. Dear presenter, you may start presenting.
Yeah, am I audible?
Yes, sir.
Hello. Yeah, my name is Ashish. Good afternoon, all. So it's my pleasure to present our research paper titled "Assessment of the Viability of Unified Large Language Model Ecosystem for Affordable and Reliable Utilization by Gen Z." So as we know that generative AI has rapidly transformed how we
Yes, sir.
learn.
Presenter?
Hello.
Your screen is
Your
not visible
screen
now.
is not presenting right now.
Okay, sorry, my mistake. Can you see?
Yes, sir.
Yeah. Thank you. As I said, generative AI has, transformed how we learn, conduct research, create content, and even solve problems. So, tools like ChatGPT, Gemini, Claude, Grok, and Perplexity have become an integral part of part of students and professionals' daily workflow. However, despite their growing popularity, users rarely depend on AI platforms. Instead, they may switch between multiple tools because each model has different strengths and limitations. This changing pattern of AI motivates our study. So, one major challenge with today's AI system is reliability. Users often encounter hallucinations, inconsistent responses, and incomplete information as well. A result many users face is to verify answers by consulting multiple AI platforms. Although this improves confidence in final answer, it introduces a new problem, such platform switching, managing multiple subscriptions, increasing cost, and additional cognitive effort. This leads to our central research question actually. Can unified LLM ecosystems address these challenges while improving user experience? So, while existing studies primarily focus on AI adaptation or user acceptance of individual AI systems, which limit research examines the feasibility of integrating multiple large language model within a single platform. So, to address this gap, we have five objectives actually, which is examining multi AI usage behavior among Gen Zs, assessing the reliability concern, analyzing the usability of challenges, understanding the role of cost, and also evaluating users' willingness to adopt unified AI ecosystems. Our conceptual framework consists of six constructs actually. Perceived reliability risk influences multi-user behavior, usage behavior. And the next one is multi-AI usage behavior affects both usability challenges and perceived usefulness. And then comes cost burden and perceived useful adaptation intention. Finally, we examine whether usability challenges also affect adaptation intentions as well. These relationships form the basis of our hypothesis. Now coming to the methodology, this study followed a quantitative research design. A structured questionnaire was distributed among 210 Gen Z respondents, and we obtained around 167 valid responses. The collected data were analyzed using IBM SPSS statistics, descriptive statistics, reliability analysis, Pearson correlation analysis. So this approach enabled us to evaluate both the reliability of our measurement scales and the relationship among the proposed variables as well. The key findings from the hypothesis was that the descriptive analysis revealed several important insights, like respondents strongly agreed that AI can sometimes generate inaccurate or unreliable response with the mean score above 4.5. Many participants also reported regularly using multiple AI tools and cross-checking answer before trusting the information. This finding clearly indicates that there is a reliability concern among multiple platform AI usage among the Gen Z users. So the next is the reliability and hypothesis result. So before testing our hypothesis, we assessed the reliability of our measurement scales. All construct demonstrated excellent internal consistency actually. With Cronbach's alpha value and above the recommended threshold of 0.70, the correlation analysis showed that 5 out of 6 hypotheses were supported. Reliability concerns significantly influence multiple AI usage. Cost burden and perceived usefulness strongly affect adaptation intention. However, usability challenges did not significantly influence users' willingness to adopt, such platform. This suggests that there is a willingness to tolerate some complexity if the platform provides sufficient value for the user. So coming to the discussion part, our findings indicates that the AI usage prioritize accuracy and trust over convenience. Instead of relying on a single AI model, they can increasingly compare outputs from multiple platforms to improve confidence. However, this behavior comes at a cost of increased complexity and higher subscription expenses. Like we know, using multiple AI platforms could, result in higher cost regarding the subscription. The study therefore suggests that future AI ecosystem should be focused not only on improving the model performance but also simplifying the overall user experience. So the next is the proposed unified LLM ecosystem. Based on these findings, we proposed a unified LLM ecosystem. Instead of maintaining separate subscription and switching across different interfaces, we could use different AI platforms in a single integrated platform. Like any models which are available for different professional and academic purposes, we can easily use it. Such systems could offer one interface, one subscription, access to multiple AI models, response comparison, improve productivity, reduce switching effort, and enhance accessibility. This approach has a potential to make advanced AI technologies more reliable, affordable, and user friendly. So, coming to the contribution part, this research contributes in three important ways. Academically, it extends existing literature by examining multiple AI usage behavior rather than single platform adaptation. Practically, it provides insight for AI developers and platform providers regarding the user expectation and future platform design. From height in a way that it highlights importance of integrated AI ecosystem that improves accessibility, efficiency, and affordability. So, coming to the conclusion part, to conclude this, our study demonstrates that the Gen Z users increasingly rely on multiple AI platforms because of concerns of regarding reliability. While this behavior improves confidence in AI-generated responses, it also creates a challenges regarding the usability and cost. Our findings indicates that unified LLM ecosystems represent a promising direction for future AI development and combining multiple AI platforms and models into a single efficient, cost-effective platform. We hope this research contributes to the ongoing discussion for the future of human AI interaction and integrated AI systems. So, thank you. That's it.
Nice presentation.
Thank you.
My question is that why did you focus on Gen Z users?
So mainly because they are the up and coming generation. And they are more tech savvy in a way that they are more exposed to the real world and they are showing much more interest in AI these days. So so Gen Z is basically the future of our next generation. That's the main reason.
How you evaluate reliability?
So reliability is that if we can see that there are different platforms which shows different outputs. When we give the inputs from one model to another, it's going to be different. So we measure the perceived AI reliability using two questionnaires items like whether AI gives inaccurate answer and whether AI responses unreliably. Respondents, rated these statements on a 5 points Likert scale, and these items formed the construct and perceived risk, perceived reliability risk in our conceptual model.
Did you consider data privacy and security?
Yes, I mean that was into consideration, but all by unifying this, like we can integrate that as well. Like to keep the study focused, like we can limit our scopes to the key factors that directly influence the adaptation of the unified AI platforms. Since it's not this was an explanatory study including additional variables like privacy and security would have made models a bit more complex. So it's
Thank you.
we have yeah,
Thank you.
thank you.
Thank you so much. Next, we have Harshit Saxena with the paper title Drug Intel RAG Domain Specific RAG for Drug Interaction Analysis. Dear presenter, you may start presenting.
Yeah, is my screen visible?
Yes, sir.
Yes.
Yeah, great. A very good evening. Myself Harshit, and today I'm going to present my research presentation on the topic drug intel RAG, which is a domain-specific RAG for drug interaction analysis. So, in the current scenario, we know that medication safety is an utmost necessity and critical aspect of healthcare. And here, drug-to-drug interactions play a major role, and they can also lead to adverse effects. They can also help us to reduce treatment efficacy and etc. However, in the current scenario, whenever we are talking about drug interactions and their information and how they interact with each other, the thing is there's always a concept of hallucinations. We know that large language models have shown strong performance in medical Q&A, but they often suffer from hallucinations and weak domain grounding, and sometimes they are not even reliable because they perform on learned patterns rather than verified clinical evidence. So that is a major shortcoming of this, which makes it very unsuitable for high stakes healthcare applications. So here we propose Drug Intel RAG, which is a domain-specific RAG framework, which is developed to provide accurate answers, which are backed by evidence, and also help us to understand more about drug-to-drug interaction analysis. So our system basically it retrieves information from a curated medical corpus, which is verified, which is clinically verified, and it uses Gemini fallback, which is the Google Gemini API, as a fallback mechanism only when the sufficient evidence is unavailable. Here, we tend to prioritize evidence-driven retrieval over generative responses in order to improve the accuracy, transparency, and the reliability of the decision support model. So first of all, we're going to start with the literature review. So these were the research papers that we studied and got our information from. So the main research paper is the first one, which is titled "Improving RAG in Medicine with Iterative Follow-up Questions." So they proposed MedRAG, which is a framework where the LLM asks follow-up medical queries on retrieval attempts and uses vanilla RAG. And their key findings involve achieving the state-of-art performance and surpassing the previous RAG prompt engineering methods, and help us to enable deep reasoning chains and flexible information seeking. However, there was some gap identified, which were first of all the cost increases linearly with query iterations, document retrieval, and if tuning option hyperparameters of also varies by model and task. So our proposed system. So this is also the research gap in which we found out in the following research papers. And most of the research papers had the same issue. They first of all they lack domain specific adaptation, weak domain grounding, due to which we would always get irrelevant answers. And they tried to always prioritize text compression, that is word to word similarity. Then they also heavily depended on the structured databases, and which provided a lot of rigidity and limited flexibility for unstructured clinical queries. And the main of argument, the main problem was high hallucination and poor fallback transparency. So in order to basically counter all these gaps, we proposed drug intel RAG. So in our proposed system, instead of relying only on retrieved documents, our system introduces a fallback mechanism, which is used as a secondary language model when retrieved results are insufficient. Here, first of all, we try to generate responses using the retrieved medical context that we have retrieved from a database. And we tend to ensure domain grounding. We tend to ensure that the answer which the LLM is generating it has a lot of information from the text only, because the text is clinically verified. So always has an advantage over the limited and generalized LLM database text. Then, whenever the retrieved text is incomplete or missing, our system switches to the fallback mechanism to avoid hallucinations. Also, here we tend to prioritize evidence. So when our the main shortcoming in the traditional RAG models was we never know how much how much hallucinations are being produced in the answers. Also, there is no transparency. Like, we don't know how much evidence from the database itself is being used to generate the answers. So in order to reduce these shortcomings, we introduce an evidence-based method in which whenever an answer is produced, we always give the evidence like high, medium, low, depending upon how much the context is present in the database. This architecture is designed to handle specific medical queries, and it is much more effective than conventional RAG systems. Also, our model basically has two modes. So the first mode is a general clinical mode, which helps us to address the general medical queries. And the second mode is the DDI mode, which is a specific drug-to-drug interaction mode, which helps us to give a well-detailed answer on how two or different drugs interact with each other, what are their adverse effects, what is their mechanism, and at the end of the day, and at the end of the answer, we also get a severity score on a scale of 1 to 10, which tells us is it beneficial to basically interact to make these two drugs interact with each other or not. So and also our framework prioritizes light work. So it is not a heavy framework. It's a light framework which helps us to, and light framework also providing accuracy. And it is very modular and scalable, which helps us to integrate different retrievers, vector databases, and language models. So this is our architecture. Basically, an user gives a medical query. So the medical query, first of all, it gets cleaned up. So here we perform normalization, and all different NLP techniques are used. For example, tokenization, word segmentation, and stop word removal, etc., to clean up the medical query and handle the medical terms. Here, the priority is given to the medical terms only, and all the extra words which do not add to the context are removed. Then this query, after this query has been normalized, we go to the vector database. For the vector database, we are using Facebook AI similarity search, and it is a medical corpus. So here, after here, all the embeddings are stored. The embeddings are stored, and the embeddings contain information about the drugs, their names, the interactions, how adverse they are, and the other data. Then after this, we tend to retrieve the context. Then after we get the retrieve concept, we calculate the evidence strength. So for example, if I give a query and I find out that the information which is used to answer this query is not sufficient in the database, then evidence is calculated, and evidence would be either high, medium, or low. So if the evidence present is high, then the answer will automatically go to the post processing, and if it is low, then it will fall back to Gemini. So here, Gemini can use its internal medical knowledge to add upon the answer, basically give more information to the context that we retrieve from our database to form a well-defined answer. And after the answer is produced, we basically filter and format it, and after that we get the final answer. So this is how our model is currently working. So this is the methodology. First of all, we made a corpus preparation, a curated medical corpus from OpenFDA. OpenFDA stands for, it's a US, it's a data set from the US, and it stands for Open Food Drug Administration, and it contains a lot of information about drug information, drug interaction. Then the query is processed, and then we generate an evidence-based response, which is generated by the LLM after calculating if the evidence present in the database is high, medium, or low. Then if if information is not available, we fall back to Gemini. If it is present, then we direct get a full answer. This is the dataset that we have used, as I already said, OpenFDA drug labeling database. We have used more than 270,000 drug labels, and our data set almost exceeded 1.4 million rows. The dataset was available as JSON files, and it can be downloaded from this site. And the various key attributes that are used in a data set are indication is usage, dosage administration, warnings, etc. Data and yeah, so as a data preparation is done like first of all the raw JSON. We cleaned up the raw JSON. Then the content was split into meaningful chunks. These chunks were then converted into embeddings using this sentence transformers and used in the face index. So here we were able to achieve an accuracy of 92%. This is our model as compared to dense BM25 and LLM only different drags. So our model gave 92% accuracy in BERT score. We use different metrics, but BERT score give the highest accuracy because BERT score is the only metric which also takes into account the semantic similarity of the answers. So here we got a 92% accuracy. Yeah, so this was our results. And the key observations are, first of all, accurate. We got accurate and evidence-based generations. Then our model reduced hallucinations because it provided transparency, as it gave with every answer basically an evidence trend estimation, like high, medium, or low. And it also helped us to explain about drug interactions using the two different modes and provided a severity levels. Our model has also been deployed. It is deployed on this app. You deployed it using Streamlit, and it's successfully deployed on cloud. And the tech stack was mainly Python, Gemini API, Facebook as similarity search, LangChain, sentence transformers. This is a screenshot of the model, how it works. So you can see it's deployed here. I asked the question, it gave me an answer. And as the question was, what happens during interaction of aspirin and warfarin? And due to the low evidence present in my corpus, as not a lot of information was present in my corpus regarding these two drugs, it gave us an evidence trend as low. And here, since you can see, I'm asking about an interaction of how two different drugs interact. So instead of answering using normal mode, the analysis mode of drug-to-drug interaction. You can also see it gave us a proper answer using mechanism, clinical risk, and recommendations. And also it gave us a severe score, which is 8 out of 10, which basically tells us we should basically not let these two drugs interact with each other because it could be really, really harmful or dangerous. So in conclusion, I would just like to say that our model drug intel RAG is a framework which is designed for reliable drug-to-drug interaction analysis. We prioritize semantic retrieval, a local medical corpus, and the main highlight is the evidence-based response generation to show transparency, to show that to minimize hallucinations, and to show that our model is it's giving answers from the verified database. And this is the amount of context that we have retrieved from the clinical database, and this is the amount of the answer that we have taken the help of from the LLM. And here, some improvements like the future work which could be done is, first of all, expanding the medical corpus. Already, our medical corpus is quite big, but we are still thinking of expanding it to inculcate more drugs and to involve more drugs. And we would also love to integrate other retrieval techniques. Here, we are using dense and fallback, but we would also love to integrate other retrieval techniques and support multiple language models. For example, here we are using only English, right? So in future, we might, if someone asks in a different language, a question, for example, Hindi or Spanish or French, then we would also love to integrate that. And also here we are using the help of Gemini only. In future, we also tend to use Gemini along with OpenAI API and Grok and other models. These are some of the references that we have used in our research paper, and so you can see, as you can see that. So yeah, that was pretty much. Thank you for listening. If you have any questions, feel free to ask. Thank you.
Nice presentation, Harshit.
Thank you so much, sir.
My question is that what evaluation methods did you use?
Sir, so as in the presentation already mentioned, we used 4 evaluation metrics: Blue, Rouge, Meteor, and BERT score. BERT score is the main metric that we've used because BERT score also prioritizes semantic similarity. For example, if I ask a question and the response is high fever or something, but when we talk about medical language, so there's no perfect answer. If there's any answer, it could be answered in 100 different terms, and they all mean the same. So BERT score is used to provide semantic similarity, and it has given us the highest accuracy of 92%. Other metrics were also used, but they were used to see how much word to word matching is there. So BERT score gave us the highest accuracy.
Okay. My last question is that can your framework handle newly approved drugs?
Yes, sir. Our model can absolutely handle newly approved drugs because we just have to add those data set of those drugs into our model. And after that training that model, we can also get a response no matter how new our drugs are. For example, as I already said, we are looking to expand our corpus, and new drugs are always being explored, like they've always been invented or explored. So it can easily handle. It just needs to be added into a database, and then the embeddings will be created, and yeah, it can handle it easily.
Thank you. Thank you.
Thank you so much, sir.
Thank you so much. Now we have Anmol Niranjan Singh Thakur with the paper title G-StitchNet Graph Isomorphism Network Driven Fragment Neural Architecture Search with Multi-Expert Single Block Distillation for Medical Image Classification. Dear presenter, you may start presenting.
Is my screen visible?
Yes, sir.
One second. So, good morning, everyone. I'm Anmol, and today I'll be presenting on a G-Stitch graph isomorphism network driven fragment NAS with multi-expert single block destination for medical medical image classification. So, this work focuses on improving neural architecture search or NAS by making architecture prediction more accurate and knowledge transfer more effective for medical image classification. So let me first explain the motivation behind this work. A neural architecture search automatically designs neural network architectures instead of requiring manual designs. A recent fragment-based NAS framework creates a new networks by stitching together fragments from pre-trained models. While effective, it has two important limitations. The first limitation that it uses an LSTM to represent architectures. Since neural architectures are actually graph structures with skip connections and parallel branches, converting them into sequences causes important structural information to be lost. The second limitation is the use of CKA for knowledge transfer. CKA measures how similar or two feature spaces, but similar representations do not necessarily means the model has learned useful knowledge. These two issues reduce both search quality and final model accuracy. So these are the limitations, as I mentioned. The first one was limitation using the LSTM, and the second one was the using of CKA. And so, as you can see in the graph, LSTM uses sequential model. So unlike LSTM, which reads architectures one block at a time, GIN represents the entire architecture as a graph. So each node is connected to every another node. So during message passing, each node gathers information from its neighbor nodes. This allows the model to understand complete network topology, including the skip connection and parallel branches. The predictor is trained using an active learning approach. Initially, few architectures are evaluated. Based on these results, GIN predicts which network new architectures are most promising. So only those are trained further. Because of better prediction accuracy, GStitch net reduces search time significantly while maintaining high performance. So the as I mentioned, we use GStitch, so it would be reducing the performance search efficiency as every node is connected to every another node, and in LSTM, so basically what will happen is in the as we can see in LSTM, let's say fragment A has to be connected to fragment D. What would happen is in LSTM when the knowledge passes one by one, sequentially basically. So first it would go to fragment A, then fragment B, so on. And but in graph, so what would happen is every node is connected to every another node. So let's say fragment A is to be connected to fragment D, so it can be directly mapped to it. So that's the benefit of having GIN
in comparison to LSTM. And the second major contribution in multi-expert single block destination or MACD is traditional knowledge distillation usually relies on a single teacher model. In contrast, MESBD learns from multi-expert teacher models simultaneously. Instead of comparing only the final outputs, MESBD performs knowledge transfer at the block level. And the first is it uses two activation functions. So the first is activation alignment loss, which makes the student feature map similar to the teachers. The second is relational alignment loss, which preserves relationships between different samples. Together, these two losses preserve functional knowledge much better than CKA alone. An easy analogy is that learning from one teacher gives one perspective, while learning from multiple teachers provides broader and richer knowledge. So this is the graph. This is the diagram how the pipeline would be working. So the first pre-trained models are divided into reusable fragments. Second, the GIN predictor searches for the best fragment combinations. Finally, the selected architecture is fine-tuned using MESBD with multi-expert features. Compared to previous NAS approaches, GStitchNet is first framework to combine graph-based architecture encoding with multi-expert block level knowledge distillation. So these are the literature review I've done, and the base paper I've taken is one second. This one, task-specific networks, the 10th one, task-specific networks using pre-trained fragments. Authors are Ashrafi and Sajedi. So they used LSTM and CKA as their, which I found that these are the limitations of this of their proposed solution. So the gap research gap analysis I found was that the LSTM predictors cannot capture non-sequential topology, and CKA is only for regularization. Geometric alignment fails to preserve functional knowledge. Then single teacher distillation. This lacks knowledge diversity from multiple expert perspectives and prior GNN approaches. So my solution is GIN predictor, then MECD, MESBD framework, multi-expert design, and heterogeneous sources. So these all collectively would increase the searching efficiency and advantages. It performs faster architecture search, improves knowledge preservation, requires very little additional computation, and can be potentially be applied beyond medical imagining. However, there are still some limitations, as I mentioned. To then these are the proposed numbers that the proposed numbers that I found by reviewing the literature and by reading the resource paper that the Ashraf ji provided. So the first the from the scratch and standard transfer learning baseline, they were on the okay, the metrics were provided in the research paper only, and the what I provide is the GStitch net. It is a proposed. I haven't like implemented it. It is proposed as I studied across the papers and from the literature reviews. And so this would be the searching efficiency, as I mentioned, like it is proposed and like although it's only a 4% increase, but in medical field, 4% is also increasing of 4% efficiency is also a very big number. And these are the advantages like substantial search quality improvement and functionality of faithful knowledge presentations, as there will be multiple fragments. Like fragments are what do I mean by fragments is that like there would be multiple pre-trained models, and what GIN would do is it would choose the best one, with the highest accuracy, and it will map it and then provide the output results. And then it would be of modular design, minimal parameter overhead, and broad applicability. Because as I mentioned, like it could be applied to beyond medical imaging. So, these are the limitations. Like of the first one would be teacher selection overhead. Like the teacher would be a pre-trained model, so it has to be the best one. Like we cannot choose any model, or and then GI and scalability as the as the cost would grow steeply with fragment library size. The more the fragments, the more the scalability issue. Then teacher availability. We need to find effective teacher, like the best one which has all the knowledge, so that we can store its knowledge base in a block. And static predictor, it would be another limitation. Then future research direction, then would be self-supervised teacher augmentation. We can use self-supervised models. Then dynamic teacher weighting. Then we can also use GANs, which like provides a discriminator and uh, with like they would synthesize the data so that we can get better accuracy. Then cross modularity, fragment transform. These can be future research directions. And for conclusion, to conclude, for GSTEDGE addresses two important weakness, as I mentioned, of fragment-based neural architecture search. First, it replaces LSTM with graph isomorphism networks, allowing architectures to represent according to their true graph structure. Secondly, it replaces CKA, which the authors mentions for regularization, with multi-expert single block tessellation, enabling better preservation of functional knowledge. So these are the uh, like these are the limitations I found on the research paper, and I propose of using LSTM and GIM. So thank you. And these are the research papers like I have taken references from.
More nice presentation.
Oh, thank you, sir.
My question is that how your model reduce computational cost?
So computational cost would be reduced first. As I mentioned, it was used earlier. It was using LSTM. So LSTM is a sequential model. So for in that, let's say we provided an image, and then there are two fragments, or let's say firstly, there are multiple models are pre-trained models are segregated into fragments, and then as a can I show you 1 second? Uh, so let's say the first in the image, the first part is about the LSTM. So let's say we can see over here that there are four fragments over here. So let's say fragment A and fragment D. These both of them are providing the best, combining the result and providing the best accuracy. So for that, the data would be going from fragment A first, then fragment B, then fragment B, then fragment C. So this would increase the time. And in GIN, what would happen is every fragment is connected to every another fragment. So what can happen is, okay, let's say fragment A and fragment D, these both are the best one that provides the best accuracy. So they would combine the result, and like we don't have to go from fragment A to and fragment A to fragment B, and then so on. And there are like permutations and combinations would be applied for every for both sequential and graph also. So which to find the best, which combination would be providing the best accuracy. So in graph, like every node is connected to every another. So that's how we can reduce the searching efficiency.
Overfitting.
Sorry. Sorry, sir. Network issue. I
How you
cannot.
overfitting?
Overfitting. So for over.
Overfitting.
Okay. Okay.
Overfitting.
Yeah. Overfitting. Right. Hello. Hello. Am I
Yeah.
audible? So
Yes.
you
Yes.
are asking
Yes.
about
Sir. Yes. Yes.
overfitting.
Yeah.
So for overfitting, we have to choose pre-trained models such that, that's one of the limitation, as I mentioned, that we have to choose the pre-trained model, which is the best for us. We have to find which can be the best one for us. Basically everything depends on the pre-trained model itself. So we'll have to find which model would be the best that can be used by us.
Thank you. Thank you.
Thank you, sir.
Thank you so much.
One second.
Now we have Dia Chogule with the paper title Incremental Data Flow Analysis Using Control Flow Graph Differencing. Dear presenter, you may start presenting.
Hello, am I audible?
Yes, ma'am.
Yeah.
Is my screen visible?
Yes, ma'am.
Good afternoon, everyone. So I'm here. My name is Diyat Saugule, and I'm here to present our work on the paper Incremental Data Flow Analysis using Control Flow Graph Differencing. So we'll have a quick look on the goal and motivation of our work. Imagine you modify just one line of Java code containing thousands of lines. But you might think this is a tiny change, but in reality, a code base contains thousands lines of code, and at the compiler level, recomputation has to take place of the entire code base. This is costly and also resource extensive. So our work simply asks question: Can we identify only the affected control flow regions and optimize just those? This question lead to the development of this algorithm, which compares two versions of the control flow graph and identify the structural differences. And you also might think there are text editors or different compilers like GitHub, which helps to identify the changes between the two versions. But it only tells us the changes at the syntactic level. But if we have to go and look at the semantic level, like on the line 2 you can see a greater than b is also means not equal to b greater than a. So if we have to look at these changes, we have to go at the control flow graph, look at the nodes and edges, and then on the basis of that we have to make the comparison. So what we will be doing is take two version of the same Java source program, that is the old version and the new version. We will generate a Jimple intermediate representation. But Jimple is a three address intermediate form of Java code. After the Jimple extraction, we'll extract the control flow graph and then perform the graph differencing. Then will the nodes which has been changed, we will only compute the data flow values of those nodes, and the path which has not been changed, we will use the old values. So we can save the time for the recomputation as well as save the resources on its usage. So let's look at the approach of the algorithm. So the output of this algorithm will be four set. First is removed node, second is added nodes, third is removed edges, fourth is removed edges. So like that, the main idea of this algorithm is, if we take a look at the CFG, there are various nodes occurring on the same line. So what our enhancement of this algorithm was grouping all the nodes which are on the same line number, which will reduce the number of nodes for comparison and reduce the redundancy. So we will take two scan. First scan will we will pass the new CFG, old CFG to get the new nodes and edges. In the second scan, we will pass the old CFG and new CFG to get the removed nodes and edges. So in the scan method, there are certain operations we will be using queue, list, and to get the edges and nodes. Let's not make things complicated, and I'll just show you the simplest demonstration by simple animation forward. So just take a look at this test case, a simple test case in which there are three print statement in a sequence 10, 20, 30. So first, what we'll be doing is ICFG extraction of all the nodes and edges. These are the nodes. This is the simple representation of the BFS traversal of all the nodes and the edges. One enhancement what we have done is in suit, if we set some options along with the nodes, the line number also is visible. Like you can see on node at line number 1, edge is from line 1 to line 3. Node at line 3 is this. So this will make things easy while debugging and also while the implementation. So now on the left hand side, you can see two versions of the code. First is the old version in the sequence 10, 20, 30, and second is the slight modification in the code 20, 10, 30. So this will give the output. The node which has been added is the one which is on the second line in the new version containing 10, and the removed node is 20 in the old version. Let's take a look how this algorithm works. So basically there will be two pointers, lookup pointer and a reference pointer. Lookup pointer will only move by one, whereas reference pointer will move unless and until a match has been found equivalent to lookup pointer, or it will reach the end of the program. First, we have to find the match for the first statement in the lookup pointer. For 10, the match has not been found. So unless and until the match has been found, we initialize reference pointer to epsilon to make things easy and correct mapping of the strings. So no match has been found. So reference pointer will move down. As match has been found, now the lookup pointer will move down and also the reference pointer will move down. So for now, as the match of the lookup pointer, we will find a match in the reference pointer for 20. As it has reached the end of the program in the reference pointer, but no match has been found for 20, this node will get added in the removed nodes. Now, similarly for 30. For 30, the node has been found, and also the lookup side, the code has been reached at the end. So the programs will stop here. Now, when we pass the old and the new version in the first scan, it will help us to find the removed nodes and edges. Now, what we will do is swap the sequence. We will first pass the new version and second the new version. We will pass the CFG of both the version, and accordingly we will find the new nodes and edges which has been added. So what are the implementation and enhancement in this algorithm? First is we added a line number by using suit libraries. So, and by using the line number, we grouped the different CFG nodes into one, which helped us to reduce the redundancy and computation. We also denoted the reference node with epsilon until the correct match has been found to correctly handle the entry mismatch case. But because of using epsilon start and we were able to handle a correct handling across different multiple methods. Second, we did not just stop by using the string equivalence, but also did semantic level equivalence. Semantic level, as in suit has different APIs. As I mentioned, in Gimple is a 3-address form. So in semantic equivalence using suit APIs, it will be compared on the basis of operator and operand, and not just string equivalence. So the lookup and lastly, the lookup and the reference pointer strategy, such that the lookup pointer will only move by one until the match has been found, and the reference pointer will keep on moving, and it will also get restored to the previous matched value if the match has not been found in the entire code. To conclude, we will be using two versions of the same program, and on the basis of that, we will only find the nodes or edges which has been changed, and then use the old data flow values as it is, and only recompute data flow values of the nodes which has been changed. So these are the reference which we have used. Thank you. We are open for your questions.
First of all, nice presentation, dear.
Thank you, sir.
My question is that how your method reduce analysis time?
Sir, because existing compiler recomputes the entire code base. Like even Java libraries has thousands and thousands and lakhs of lines of code. But even if the developer make a small changes, what happens is entire recomputation takes place. So we just have to map the changed sentence or line and only recompute that and use old values as it is. So that will reduce the time.
Then how you detect changes in the CFG?
Uh, we grouped the nodes which were having the same line number, and if the node in the old and the new version the node equivalence is found, then that simultaneous node will get added into the new removed node or new node, like that.
Tell me any tool you use, name of the tool.
Suit and Spark.
Thank you.
Thank you, sir.
Thank you so much. Now we have Vidhi Jadhav with the paper title Kernel Domain Adaptation for Graded Disaster Damage Mapping. Dear presenter, you may start presenting.
Actually, ma'am, I'm not able to share my screen.
Ma'am,
Yeah,
can you try now?
yeah. Yeah, is it visible now?
Yes, ma'am.
My Jadoo, and today I'll be presenting my work titled Kernel Domain Adaptation for Graded Disaster Damage Mapping. Uh, just a sec. Yeah, so this work basically focuses on doing disaster assessment automatically using
Dear presenter, your voice is inaudible.
yeah. Hello.
Ma'am, your voice is not audible.
Am I audible?
Your voice is
Hello.
breaking, ma'am.
Am I audible now?
Yes, ma'am.
Okay. And is my screen visible?
No, ma'am. Yes, now it's visible.
Okay. So, since the humanitarian organization must respond rapidly and effectively, and this can be done by taking help from satellite images. But the thing is, manually annotating these images can be time consuming and labor intensive. And also because of the disaster, the structural destruction, environmental changes, lightning sensor, the data distribution keep changing. This is called the domain shift. So basically, the challenge of domain shift motivated us to develop a strong, robust framework that can deal with a different type of, or we can say different disaster scenario. Because there are some traditional model, they work well when trained and tested on the same type of data set, but they lack when disaster scenario change. So uh, only strong KDA framework stands for kernel domain adaptation that can help model to generalize even if the disaster scenario changes. So the our objective is to build a framework then that can automatically assess the damage area and reduce the domain shift. And to achieve this, we employ kernel domain adaptation using MMD based feature alignment, kernel PCA for feature transformation, and an SVM classifier for final damage predictions. So these are some of the research papers that we have gone through. We have divided them into a different category as per the method they have used. So most of them have used transfer learning, domain adaptation, kernel methods, uncertainty estimation, graded damage mapping. So most of them either perform binary damage classification, require large amount of label data, or fail to generalize across different disaster domains. So based on this observation, we identify that the major challenge is domain shift. So, our proposed framework address this limitation through kernel-based feature alignment while supporting multi-level damage classification. This is the proposed methodology. So it starts with two domains, source and target domain, where source domain contain labeled pre-disaster images and target domain contain unlabeled post-disaster images. So here source domain works as knowledge base. So our aim is to transfer the knowledge from source domain to target domain to reduce the domain shift. So next phase is feature extraction. So here what we are doing, basically we are converting the raw image pixel into the numerical feature, what we can say feature representation, so that basically a machine learning model can understand the whole process and understand the data that we are using. And the second step is Gaussian kernel transfer learning, which is basically a core idea of this whole architecture. The feature that we have extracted in the previous phase, we are taking that features and we are projecting them into high dimensional nonlinear feature space. Because the data set that we are using, the satellite images, they have so many complex relationship. So the GKTL, this kernel can basically understand the relationship, non-linear relationship, and help the model works accordingly. And another thing is multi-kernel fusion. So we could have used a single kernel fusion also, but the thing is a single kernel will only what we can say only observe one relationship among the data set. But here we are using the multi-kernel so that we can have the multiple and dynamic observation among the data set. And the damage classification. So after detecting the damage, how much damage is there? So we are basically grading the damage into different level, like no damage, minor, major, and fully damaged, like that. So basically, this is the data set we have used a single sample that I have mentioned here, pre-disaster and post-disaster images. So each image comes with this JSON file. So basically, these files provide the corresponding damage labels used for supervised training and evaluation. And this is the implementation methodology. So I will elaborate the whole procedure. So it starts with loading the data set and then parsing the annotation file. So each disaster image comes with JSON file that I mentioned. So this contain building polygon, damage label, object type. So then next step is we are converting this large image into small tiles because satellite images are extremely large. So we really need to split them into patches. So because large images require huge memory and high computation, whereas small tiles allow localized learning and faster processing. And another step is feature extraction. So we are extracting different type of features using like color histogram, converting them into grayscale. Then we are extracting gradient features and statistical features also. Then we are dividing the whole data set into two domains, source and target domain. And then we are splitting them into train and test size. Like for example, 5% for training and 95% for testing like that. Then feature scaling. So to normalize features because without scaling, histogram values dominate small features. So where scaling makes all features comparable. So here we are basically scaling the features. And then it comes domain adaptation, where we are using MMD alignment. So the main idea behind kernel domain is move source distribution closer to target to reduce the domain shift. Then kernel PCA. So projecting data into non-linear space because satellite image is complex and non-linear. So we are utilizing the kernel PCA here. Then we are training the SVM because SVM works well for medium data set, high dimensional feature, and the data set that contain non-linear boundary. So we are using the SVM classifier, and then we are evaluating the whole system by using metric, and the purpose here is to compare the baseline model to domain adaptation because many traditional model utilizes baseline model, but here we are proving that domain adaptation means adapted model works better than the traditional baseline model. So this is the result that we have achieved. So the table shows that we compared our proposed framework with the baseline, which one is the traditional model, RBF SVM classifier. So the baseline achieved an accuracy of approximately 83, whereas our proposed framework achieved 95.97%. So this improvement shows the effectiveness of domain adaptation. Second one is the class-wise evaluation shows excellent performance for no damage and destroyed categories, where minor damage and major damage remain more challenging because they share similar visual characteristics. Uh, this one is about we also here we also evaluated the model under different training data percentages. These experiments demonstrate how the framework performs when labeled data is limited. So as the more training data becomes available, the effectiveness of domain adaptation increases. And this one is this study confirms that both kernel PCA and MMD contribute significantly to the final performance. So as you can see, the first one we have only utilized a baseline RBF SVM where it has given the accuracy of 80 nearly 83%, and we are adding each component and we are getting the higher accuracy. So in conclusion, we developed a kernel domain adaptation framework for graded disaster damage assessment. The proposed approach successfully reduced domain shift and significantly improves classification performance over the baseline. and the framework achieved an accuracy of 95.97%, demonstrating its effectiveness for automated disaster damage mapping. And if I talk about the future work, the future work we plan to integrate Markov state modeling to capture temporal damage progression, because here we have the data set we have used, which are the handcrafted, so the model should be able to perform according to temporal damage progression. So we also aim to extend the framework using deep transfer learning technique and evaluate it on a large multi-disaster data set. So yeah, these are the references, the researches we have gone through. So yeah, that's it from my side.
Nice presentation, Vidhi.
Thank you, sir.
Question is that how your method handle domain shift?
Sir, as I mentioned, the previous traditional model, they were using baseline. If I talk about the pipeline of that traditional model, they were only focusing on domain data set, because the domain data set have labeled features. But the adapted model that we have utilized here, it is combining the data set from both domain source and target domain, and then it is making prediction. So the different scenario, environmental changes, structural destruction, everything has been included. The model has already been trained on that combined data set.
What is your size of data set? What is the
Sir,
size of
actually,
data set?
the data set, yeah, sir, the data set I've used like two different type of data set, tornado and hurricane. So the data set is very large. So I've taken 100 samples out of them. So 100 means it is 200, like one for pre-disaster and same for after post-disaster image. So yeah,
Thank you.
yeah,
Thank you.
yeah,
Thank you.
sir, yeah. Thank you, sir.
Thank you so much. Now we have Kusum C with the paper title Melanoma Identification Using Deep Learning and Ayurvedic Recommendation System. Dear presenter, you may start presenting.
Yes, ma'am. I'll share my screen. Ma'am, is my screen visible?
Yes, ma'am.
Good afternoon, everyone. Thank you for the organizing committee for the opportunity to present today. My name is Kusum C, and I'm presenting our work titled Melanoma Identification Using Deep Learning and Ayurvedic Recommendation System, co-authored with Dr. Bhageshri SR, Professor Raghavendra YM, and Professor Rajesh KM. This project brings together two very different worlds, modern deep learning and traditional Ayurvedic medicine, to build a system that doesn't just detect melanoma but also guides user towards a natural holistic treatment path. Let's start with why this matters. Skin disease affects nearly 1.9 billion people globally every year, and melanoma alone accounts for roughly 3,25,000 new cases annually. Despite this scale, we found essentially zero existing AI tools that pair an accurate diagnosis with any form of treatment guidance. Most allopathic treatments offer fast relief, but they often rely on chemical formulations. Prolonged use, for instance, can cause skin thinning and recurring inflammation. And traditional dermatology still depends heavily on subjective, time consuming visual examination, a real bottleneck in rural areas and undeserved regions. So the problem isn't just can AI detect skin disease? That's fairly well studied. The real gap is what happens after detection. This chart shows the global prevalence of skin diseases by region. Asia alone counts for nearly 900 million cases, and not coincidentally, this is also a region where access to dermatologists is often limited. Three things motivated this work. First, Asia carries the heaviest burden, frequently with the least specialist access. Second, incidence is rising across every region, which increases the need for scalable, low cost screening tools. And third, this is the key insight deep learning can already approach dermatologist level diagnostic accuracy, but it almost never tells the patient what to do next. That's the exact gap our system is designed to close. We reviewed several recent studies in this space. Esteva et al. Achieved dermatologist level accuracy with CNNs, but their system is decision support only, no treatment plan. The next author built strong ensemble models, but again, detection only. Jane's 2024 review noted that AI has improved diagnosis but still lacks personalized treatment support. And Sinha et al. DermSynth 3D addressed the data scarcity problem, but not the treatment gap. The pattern across literature is consistent. Diagnosis has advanced significantly, but no system integrates AI based detection with a structured, natural treatment pathway. That's precisely the space we are working in. So, here's our proposed system overview. And it literally comes down to combining two complementary halves. On the AI side, we use CNN based feature extraction, transfer learning through EfficientNet BO and MobileNet V2, the Adam optimizer with data augmentation for robustness, and we deliver instant classification through a web interface. On the Ayurvedic side, we ground the recommendations in the classical framework of balancing Vata, Pitta, and Kapha, and we surface herbal formulations like turmeric, neem, ashwagandha, guduchi, along with personalized dietary and lifestyle guidance. Importantly, the system also includes precautionary guidance and a clear referral to a doctor in severe cases, so it never tries to replace clinical care. Together, these two halves form a single pipeline, accurate detection plus a responsible, natural next step. This is the full pipeline, end to end. We start with data collection, focused specifically on melanoma, move through pre-processing, then feature extraction using CNN backbones, model training, model evaluation, and finally deployment as a web application that pairs each prediction with Ayurvedic remedies. Each stage feeds directly into the text, and I'll walk you through the key stages in a bit more detail over the next few slides. Our melanoma dataset was drawn from open access dermatology sources and verified medical repositories covering different skin tones, age groups, and lighting conditions to improve real world robustness. On the pre-processing side, we applied four key steps: resizing every image to uniform 224 by 224 resolution, normalization of pixel values to a 0 to 1 range to stabilize training, data augmentation, random rotations, flips, and brightness shifts to improve generalization, and Gaussian blur based noise reduction to sharpen edge features. This combination of enhancement and augmentation is something many earlier studies skipped, and we found it made a real difference in handling inconsistent lighting and backgrounds. For the core models, we compared two transfer learning architectures. MobileNet V2 uses depth-wise separable convolutions and inverted residual blocks. It's lightweight and fast, well suited for web-based predictions. EfficientNet B0 uses compound scaling to balance network depth, width, and resolution, which lets it capture finer lesion detail. Training was done over 10 epochs with a learning rate of 5e to 05, batch size of 32, and the Adam optimizer with beta values of 0.9 to 0.999, along with the linear warm-up scheduler. The stack itself was built on PyTorch, Fast API, and Jinja 2 for the web layer. EfficientNet B0 achieved 96.92% accuracy compared to 93.84% accuracy for MobileNet V2. Beyond the raw number, EfficientNet B0 also converged faster during training and consistently produced lower validation loss, meaning it was learning finer lesion textures more efficiently across the 10 epochs. MobileNet V2 is still strong option. It's faster and lighter, but for accuracy, critical use cases like melanoma screening, EfficientNet V0 was the clean winner in our evaluation. Looking beyond accuracy alone, EfficientNet V0 led across every single metric: an F1 score of 0.96, precision of 0.97, and recall of 0.95, compared to 0.93, 0.94, and 0.92 respectively for MobileNet V2. The precision and recall numbers matter most here clinically. High precision means fewer false positives, and high recall means fewer missed melanoma cases. In a screening context, missing a real case is the costlier mistake, so this recall figure is particularly encouraging. Here's what the actual user experiences looks like. A user uploads a skin image through our Fast API and Jinja 2 based interface, receives an instant classification with a confidence score, and then sees an Ayurvedic explanation, herbs, diet, and lifestyle guidance tailored to the prediction, along with precautionary advice and a referral to a doctor if the case looks severe. A few observations stood out during development. EfficientNet V0 consistently outperformed MobileNet V2 across over diverse data set. The variations in skin tones, ages, and lighting in our dataset directly improved real-world reliability. And most importantly, by pairing the prediction with an explanation and a natural remedy, we are closing the diagnosis to treatment gap we identified earlier in our literature review. So this is the output screen which our project has achieved. This is the melanoma prediction output screen where we have achieved 90.91% accuracy. Looking ahead, we have identified four clear directions: expanding the dataset further to reduce bias, adding explainable AI modules so prediction are more transparent and clinically trustworthy, extending multilingual and mobile support for broader accessibility, and eventually incorporating real-time camera-based detection. To conclude, this project shows that by merging deep learning diagnosis with Ayurvedic treatment principles, we can move beyond simple detection towards accessible, sustainable, and genuinely patient centered dermatological care. Thank you very much for your time. I'd be happy to take any questions.
So first of all, nice presentation, Ms. Kusum.
Thank you, sir.
My question is that what data set you used for training?
So we have used the skin disease images of melanoma deceased patients for training, and it was a 70% and 30% like for the training and validation percentages if to be given. The images were around 400 approximately. They were used for that.
Next question is that how are Ayurveda recommendations generated?
So they are rule based for now, but we are training it more and more to make it AI like the real time prediction thing.
Any limitation of your period?
Sorry, sir.
Any limitation of your period?
Yes,
Any
sir. That I said that we can make it.
hello?
Sorry, sir.
Any limitation of your period?
Yes, sir. There are certain limitations. Like we can expand the data set. The data set is less for now. Like it may give wrong predictions sometimes. We can make it multilingual as it is only English in English, and we can make it to mobile support app. Now currently it is only a website. Then we can also make it a real time camera based detection as well. So these are the some of the limitations which we have.
What is the size of your data set?
Sir, 400 images approximately, 70% for the training and 30% for the validation.
Thank you.
Thank you, sir.
Thank you so much. Now let's have Madhuvarsu Subhash Chandra Mandit with the paper title Multimodal Self-Supervised Learning for Autonomous Driving Perception. Dear presenter, you may start presenting. Okay. Next, we have Vaishnavi Lakade with the paper title Visual Speech and Textual Authentication Using Deep Learning Algorithms. Dear presenter, you may start presenting.
Yes, ma'am. Am I audible?
Yes, ma'am.
Okay, ma'am. So, good afternoon, everyone. I am Saili Lagat, and along with my teammates Vaishnavi Kumkhele, Vaishnavi Lakde, and Mohammad Saad Siddiqui, and the guide of our project was Professor Vishal Jaiswal, sir. So, this project focuses on detecting modern AI powered cyber threats such as phishing emails, deepfake videos, and in future, voice phishing attacks. So, with the rapid advancement of AI, cyber attacks have become much more sophisticated. Today, attackers can generate convincing phishing emails, realistic deepfake videos, and clone voices capable of deceiving even experienced users also. Traditional security systems are designed to detect only one type of attack at a time and making them ineffective against modern multimodal cyber threats. So, to overcome this limitation, we developed this VISTA, which stands for Visual Speech and Textual Authentication, which is an AI driven authentication system capable of detecting these both phishing emails and deepfake videos through a single integrated platform. So, let's understand what exactly the problem is. Every day, millions of phishing emails are sent worldwide, resulting in financial fraud and identity theft. At the same time, AI generated deepfake videos are increasingly being used for misinformation, information, digital.
Video.
Sorry.
Okay.
Most
Carry on.
existing cyber.
Carry on. No issues.
Yes, sir. Most existing cybersecurity tools specialize in detecting either any one module like phishing or deepfake, but not both. So this creates a significant security gap. Our motivation was to develop one intelligent platform which is capable of detecting multiple forms of AI generated threats simultaneously and thereby improving digital trust and online safety. So these are some of our project objectives. The first objective is phishing detection, where we analyzing email content using NLP and ML techniques to determine whether an email is genuine or malicious. The second main objective is defect detection, where we analyzing video frames using deep learning techniques to identify manipulated videos. And the third and the main thing is integration of all these modules into a single platform that provides accurate, speed, and usability for real world deployment. So, this is our project system architecture. So, this illustrates the overall architecture of our system. You can see here there is a user, and the first module processes textual data for phishing detection. The second one is deepfake, which takes either video data for deepfake detection or image, and each module independently predicts whether the input is authentic or malicious, and the final results are displayed through a unified interface via our browser extension, and making the system easy to use while maintaining high detection accuracy. And now I would like to hand over the presentation to my another teammate who will explain the technical implementation and results in further slides. So thank you. Vaishnavi.
Thank you, Saili. Now I will explain the implementation details and performance of our system. So for phishing detection, we first pre-process the email text. This includes removing unnecessary characters, converting text into lowercase tokenization and normalization. After pre-processing, we will apply the doc2vec, which converts the textual information into the meaningful numerical vectors while preserving semantic relationships. So these vectors are then given to a random forest classifier A random forest classifier consists of multiple decision trees that works together to classify emails as either phishing or legitimate. So this approach provides a robust performance with good generalization capability. Okay. So now defect detection. For defect detection, the uploaded videos is first divided into the individual frames. So each frame is analyzed using a multi-layered convolution neural network or CNN. The CNN detects subtle facial inconsistencies such as unnatural blending, lightning, variations, facial distortions, and manipulations artifacts. So the outputs from multiple frames are combined to determine whether the video is real or deepfake. So these frame level analysis significantly improves detection accuracy. Okay, so this is the performance matrix and result for our system. So our phishing detection module achieved an accuracy of 90% using Dr. and random forest. The defect detection module achieved 92% accuracy using multi-layered CNN. Additionally, the average processing time is less than 1 minute, enabling practical real-time deployment. And these results demonstrates that our system is both accurate and efficient for modern cybersecurity applications. Okay, so here are the advantages and impact of the Vista. So Vista offers several important advantages, including it provides protection against both phishing emails and deepfake videos within a single platform. Secondly, it combines machine learning and deep learning techniques to achieve high detection accuracy. Third, it optimizes the architecture that enables fast threat analysis suitable for real-world deployments. So looking ahead, we plan to extend the project by adding a phishing detection module capable of identifying AI-generated voice scams. We also plan to develop mobile and web dashboards, implement real-time alert systems, and integrate transformer-based AI models for even greater accuracy. Okay, so here is a future roadmap and expansion. So it has like phishing detection model, real-time alerting, advanced AI integration, and cross-platform dashboards. Okay. So to conclude, Vista demonstrates how artificial intelligence can be used not only to create sophisticated cyber attacks but also to defend against them. So by integrating phishing detection and defect detection into unified platform, our system enhances cybersecurity, improves digital trust, and provides scalable foundation for future multimodal threat detection. So thank you for your valuable time and attention. We would be happy to answer any questions.
Hello. Hello. Hello.
Yes, sir, you're audible.
Yeah. Nice presentation, all of you. My question is that mm, how you handle noisy data or poor quality images?
Sir, basically we are using multi-layered CNN. So in multi-layered CNN, basically we are getting some input as an image or as a video. So if the image or video is having a poor quality, then we are trying to fix it using. So that is why we are applying it multi-layered CNN. So all of these frames are divided into smaller parts, and we are adjusting those frames in such a way that can help our model to analyze it clearly. So that is where we are handling.
Can your system work for real-time applications?
Yes, sir. So currently we have designed a browser extension for this system, for this multimodal system, and we are trying to deploy it in real-time work areas like in ERP systems or in newsrooms or in banking applications also. So currently we are in testing phase. We will also try to deploy it.
Okay, thank you.
Thank you, sir.
Thank you so much. That was the last presentation for today. I would sincerely like to thank our authors for their excellent presentations and their contribution to this session, and all our participants for being a part of this international conference. I hope this session was informative enough. We, on behalf of the whole team, thank you for the support during the 11th version and all the previous 10 versions of the conference. We will be happy to have you in the 12th version in 2027. All the presenters would be getting their digital certificates through email within 2 working days. The publication will be live within 7 to 8 months. Kindly cooperate with the team of ICT4SD 2026. I would also like to thank our session chair, Professor Ajay Kumar, for chairing this session. This is a small token of appreciation to the chair on behalf of the team of ICT4SD 2026 and Global Knowledge and Research Foundation and partners. Thank you so much, sir. Do you
Thank
have
you.
any
Thank you.
closing remarks for the session today?
I think I sincerely thanks to all the authors and participants for this valuable contribution. I think out of 10, 9 are successfully presented. The presentation reflected excellent research, innovation ideas, and meaningful discussions. My heartfelt thanks to our moderator. Special thanks to our Amit Joshi sir. Thank you all.
Thank you so much, sir. I would request everyone to switch on their cameras for a quick snapshot. Thank you everyone for being a part of this conference. Stay safe and take care.